This is the third video in the topic on how does a hot air balloon work. In this video we're going to be looking at Archimedes' principle and the buoyancy force.
So in this lecture we're going to consider Archimedes' principle and the buoyancy force. In the previous video we saw that there's a weight force pulling our hot air balloon down, and we need some force to overcome that weight force to make our hot air balloon fly. So that force is the buoyancy force. Now there's a nice story behind how this buoyancy was discovered. Archimedes of Syracuse was set a puzzle by King Hero. King Hero had ordered a crown from a goldsmith. He gave the goldsmith a whole lot of gold to make the crown, but he didn't entirely trust the goldsmith. He was a bit worried that the goldsmith might have mixed some silver in with the gold to create the crown. And so King Hero gave the crown to Archimedes and said, "Archimedes, can you find out if this is pure gold or not, but make sure that you don't destroy the crown." Archimedes was very perplexed about how to do this. And then one evening he decided to have a bath. He got into the bathtub and noticed that the water rose. Now the story goes that he got so excited by this that he jumped out of the bathtub and ran through his city naked, going, "Eureka!" And apparently this was the first eureka moment in science. What Archimedes had realized was that the volume of the water displaced by him was equal to the volume of his body. So he could use this method to work out the exact volume of the crown. If he put it into water and measured exactly how much the volume changed, then he'd know exactly the volume of the crown. And gold has a density which is different to the density of silver. So density in physics has the formula: density is equal to the mass divided by the volume. So generally we give the density the symbol rho, the Greek letter rho. So we can write this equation as rho is equal to little m over capital V. And Archimedes realized that if he found out the volume in this method of the crown, and then he found out the mass of the crown just by weighing it with some scales, he would know the exact density of the crown, and this would tell him if it was made from gold or if the gold had been diluted with silver. Now it's possible, unfortunately, that this is just a story, because back then it would be very, very hard to measure the volume difference between the volume of water displaced by gold and the volume of water displaced by silver. But it's still a nice story. Okay, so let's have a look now at a calculation that we can do using this density equation.
So the question is, Archimedes read the volume of a bucket of water to be 10.222 litres. He then placed the crown into the bucket and noticed that the water rose to a volume of 10.273 litres. The crown had a mass of 894 grams. Now, is the crown made of pure gold? And if not, what fraction is silver and what fraction is gold? And we're told that the density of gold is 19.30 grams per centimetre cubed, and the density of silver is 10.49 grams per centimetre cubed. So let's start by working out the density of this crown. That will tell us if it's made of pure gold or not. So to work out the density, we're going to have to use the density is equal to the mass over the volume. So we'll need to start by working out the volume of the crown. So the volume is equal to the final volume of the bucket of water minus the initial volume of the bucket of water. So that's 10.273 minus 10.222. And so that is equal to 0.051 litres. Now these densities are in centimetres cubed, which is millilitres. So to convert this into milliliters, we need to times it by 1,000. So the volume of the crown is equal to 51 centimeters cubed. Or we could write milliliters here if we want. Those are the same units. Okay, so we've now got the volume. So now we can get the density. The density is equal to 894 grams over 51 centimeters cubed. And so this gives us a density of 17.5 grams per centimeter cubed. So you can see this is less than the density of gold. So this tells us the crown is not made of pure gold. Okay, now we're going to need to clear some space to work out what fraction of it is silver and what fraction of it is gold. Okay, so we've got that the density of the crown is equal to 17.5 grams per centimeter cubed. The density of gold is equal to 19.30 grams per centimeter cubed, and the density of silver is equal to 10.49 grams per centimeter cubed. The other thing we knew was that the volume of the crown was equal to 51 centimeters cubed. Now we know that the crown is made up of the volume of gold plus the volume of silver, which went into making it. So we can say that the volume of gold in the crown is equal to 51 centimeters cubed minus the volume of silver. So that's one equation we've got. Let's call that equation 1. Now the other thing we know is the mass of the crown. So we know that the mass of the crown is equal to the mass of the gold in the crown plus the mass of the silver in the crown. So the mass of gold in the crown is the density of gold times the volume of gold, and the mass of silver is the density of silver times the volume of silver. So we've got that the mass of the crown is 894 grams, the density of gold is 9.30 times the volume of gold, and the density of silver is 10.49 times the volume of silver. So what we've got now is two equations that we're going to have to solve simultaneously. So this is getting a little bit complicated, but all we need to do is replace this volume of gold here with this equation here. So we've got 894 is equal to 19.30 times the volume of gold, which is 51 minus the volume of silver, plus 10.49 times the volume of silver. And so we've got 894 is equal to 19.3 times 51, which is 984.3 minus 19.30 times the volume of silver, plus 10.49 times the volume of silver. Now we're going to need to do some algebra to rearrange this. We'll move the two terms with the volume of silver over to the left-hand side and move all the terms with just numbers over to the right-hand side. So we've got 19.30 times the volume of silver minus 10.49 times the volume of silver is equal to 984.3 minus 894. And so we can take the volume of silver out as a common factor here. And what we end up with on this side is 8.81 times the volume of silver is equal to 90.3. And so the volume of silver is 19.3 divided by 8.81, which is equal to 10.2 centimeters cubed. And the volume of gold from this equation here is just 51 minus the 10.2, and so that gives us 40.8 centimeters cubed. So there's 4 times as much gold as silver, so this combined tells us that it's 1/5 is silver and 4/5 is gold. And so if these were the values that Archimedes really measured, then the goldsmith had cheated King Hero.
Let's measure the density of the green bottle and the red bottle now. To measure the density, we need to work out the mass and also the volume of these two bottles. So using Archimedes' method, we can work out the volume of water displaced by the bottle when we submerge it. So at the moment, this beaker is saying that there are 3,000 millilitres of water in here. Let's now submerge this red bottle. It's now saying that there are 3,600 millilitres of water in the beaker. So this bottle has a volume of 600 millilitres. Now to get its density, we also need to measure its mass. So let's take the handle off and we can weigh it. It has a mass of 1.2 kilograms. So to get the density, we do the mass, the 1.2, divided by the volume, which was 600 millilitres. And so this tells us that the density is equal to, we get 2 kilograms per litre. So that's quite a lot more dense than water. Let's now check this much lighter green bottle. When we put this one into the water, the volume is displaced up to 3,600 millilitres. So this has a volume of 600 millilitres. Let's now check its mass. The mass of this one is 30 grams. So 30 grams divided by 600 millilitres. So 30 grams divided by 0.6 litres gives us 50 grams per litre or 0.05 kilograms per litre. So this one is much less dense than this one. Now one other interesting thing to note is that when we submerge this, the volume increases by 600 millilitres, but the mass on the scale also goes up by 600 grams. Now this is actually because of a reaction force. This water is providing a buoyancy force to the bottle. So the buoyancy force provided on the bottle is the weight of the bottle times the volume. So the buoyancy force it provides to the bottle is equal to rho Vg, and so that's proportional to the volume. Now to get that buoyancy force, there's an associated force of the bottle pushing downwards on the scale. And so the scale actually reads an extra 600 grams, which is equal to the mass of that water which is displaced by the bottle. With the red bottle, we get the same reading on the scales. It's also changed by approximately 600 grams because we've got the same mass of water displaced. It doesn't matter about the different densities. If I let go of this handle, the reading goes up a lot because we've added the extra weight force from the red bottle. Archimedes' principle is that the upwards buoyancy force on an object is equal to the weight of the fluid that the object displaces. So have you ever wondered why when you get into a swimming pool it feels like you are floating, and then if you get into seawater it feels like you're floating even more? Well, this is because your body has volume. When you get into the water, you're displacing a certain volume of water. And so there's a buoyancy force on your body. And that buoyancy force is equal to the weight of the water that your body displaces. Now you may have heard about the Dead Sea, which is near Jordan. The Dead Sea has an especially high density. If you have a metre cubed of water from the Dead Sea, that's got a density of 1,240 or that would have a mass of 1,240 kilograms, whereas fresh water, if you have 1 meter cubed, weighs 1,000 kilograms. So in the Dead Sea, people float even more because the density of the Dead Sea is very close to the density of the human body, and so you float without even trying in the Dead Sea. So let's go back to considering hot air balloons. Hot air balloons have a buoyancy force because they displace some of the air. As we'll see with the ideal gas law, there is air inside a hot air balloon, but the air inside the hot air balloon is less dense than the surrounding air. So another example of this is actually with helium balloons. So let's look at a helium balloon now. Here's a helium balloon. This is filled with helium gas, which is much less dense than the surrounding air, which is mainly nitrogen molecules with a few oxygen molecules. So this helium balloon will float if I let go of it. And when I let go, it accelerates up towards the ceiling because the buoyancy force is much greater than the weight force. So there's two forces acting on this helium balloon. It's got the buoyancy force pushing it up, and it's got the weight force which is pulling it down. Now one very important rule in physics is that for a body to be stationary, all the forces acting on it have to be in equilibrium, which means that all these forces need to cancel each other out. So if we add mass to this helium balloon so that we're increasing its weight, we can make that weight force, the downwards force, equal to the buoyancy force, which is the upwards force. So to add weight to it, let's tie this piece of cardboard to the helium balloon's string. There we go. So now when I let go of the helium balloon, it's slowly accelerating downwards as the weight force, the downwards force, is now larger than the upwards buoyancy force. So what we can do now is we can snip off little bits of the cardboard to decrease the weight force until these two forces are equal. Okay, still going downwards, so we need to snip off a little bit more. Going downwards, but accelerating more slowly. Going downwards very, very slowly, so just a little bit more. Very, very, very slow downwards. And now the helium balloon is in perfect equilibrium. It's staying exactly where I put it. So now let's do a calculation involving this helium balloon.
So the question is, a balloon has a volume of 3.50 litres. The mass of the balloon and string is 2.0 grams. It is filled with helium with a density of 0.1786 grams per litre. If air has a density of 1.22 grams per litre, what minimum mass must be tied to the balloon to stop it from floating away? Okay, so let's consider what's going on. Here we've got our balloon. Now the balloon's got a buoyancy force upwards, and this buoyancy force is equal to the weight of air displaced. That's Archimedes Principle. And downwards we tie on a mass, and it's got a weight force. Now to stop the balloon flying away, this buoyancy force and this weight force need to be equal to each other. If the weight force is larger than the buoyancy force, then the balloon will not fly away, but the limiting case with the minimum mass is when the weight force is equal to the buoyancy force. So let's start by working out the weight force. So there's three things contributing to the weight force, three masses. We've got the mass of the balloon plus the string, which we're told is 2.0 grams. We've then got the mass, which we tie onto it, which we need to find. So let's call that M. And then finally, we've got helium inside the balloon. And so we've got the mass of that helium as well. So that's the density of helium times the volume of the balloon. And then to make it into a weight force, instead of just a mass, we need to multiply that by G. So the density of helium is 0.1786. The volume of the balloon is 3.50 litres, and so we have the mass of the helium inside the balloon is equal to 0.625 grams. And so we've got 2.625 grams plus the mass in grams times G will be our force in millinewtons. Okay, so now what we need to do is work out this buoyancy force. So the buoyancy force is just equal to the weight of the air displaced. So that is equal to the mass of the air times G, and the mass of air is the density of air times the volume of the air, which is displaced, times G. And so this is equal to 1.22 times 3.5 times G. And so this is equal to 4.27 G. Now what we've said is that our buoyancy force must be equal to our weight force. So we can set this one here equal to this one here. So we have 2.625 plus M times G is equal to 4.27 G. These G's cancel out. Now all these masses are in grams, and so our final mass is 4.27 minus 2.625. So this gives us 1.65 grams is the mass that must be tied to the end of the balloon there.
Now the same principle applies to boats as well. Boats float because they displace a certain weight of water. The weight of water that a boat displaces is equal to the weight of the boat. So if you have an oil tanker which is full of oil, it'll float very low in the water. If you have an empty oil tanker, on the other hand, it'll float much higher and will displace a lot less water. Let's have a look at a demonstration now involving boats. Here's a problem for you to try. This is called the fisherman's puzzle. Imagine that we have a lake like this beaker of water, and there's fishermen with all their anchors and everything in a boat on the lake. There we go. Now we'll mark the height of the lake with a pen here so you can see what the water level is. Now the fishermen are having a bit of a debate on the boat. Some of them are saying, well, if we jump out of the boat, we'll be taking up the same volume of water as we would in the boat, so the volume of the water won't change. And others are going, oh no, hang on. If we jump out, we're more dense than the surrounding water, so we'll displace less volume and the volume of the lake will sink. So have a think for a minute. What is going to happen if these fishermen, which are more dense than the surrounding water, jump out of the boat and into the lake? Okay, hopefully you've now had to think about what will happen. Let's do the experiment and see what happens to the volume of the lake. Okay, the volume of the lake has dropped significantly. Now that's because these objects are more dense. And so when they sink to the bottom, they displace less water than their weight force. So in this case, their weight force, the downwards force, is larger than the buoyancy force, the upwards force. So now they displace less water. When they were in the boat, they caused the boat to sink so that the volume displaced by the boat had the same weight as the weight of all the objects together inside the boat. So a similar thing happens with icebergs. When ice freezes, it's actually unusual and it expands as it freezes. So ice is less dense than liquid water. This is why icebergs float. So that's why we have the North Pole. The North Pole is formed entirely of ice. With icebergs, a large percentage of the iceberg is found under the water because the density of ice and the density of water, while different, are not especially different. So let's have a look at a demonstration now of an iceberg.
Okay, so what we're doing in this case is we've got an ice block, and let's say that it's got some volume V of ice, and we're floating it in fresh water. So we know that the density of the ice is equal to 0.9167 grams per centimetre cubed, and that the density of the water is equal to 1.000 grams per centimetre cubed. Now if this was salt water, it would be slightly more dense, but in this demonstration it was fresh water, so we're going to be using fresh water in our calculation. Now we know that the net force acting on our ice block is 0 because the ice block is not moving. So we've got a buoyancy force pushing the iceberg up and a weight force pushing the iceberg down, and these two forces must balance each other or the iceberg would accelerate, and it's not accelerating, it's remaining stationary. Okay, so the buoyancy force is equal to the weight of the water displaced. So we can call this volume here, let's call that V water. That's the volume of the water displaced. So the buoyancy force is equal to the mass of the water displaced times G, which is equal to the volume of the water displaced times the density of the water times G. And the weight force for the ice block is just equal to the mass of the ice times G, which is once again just equal to the volume of the ice block times the density of the ice times G. So now what we want to equate is this part here and this part here. So we've got that the volume of the water times the density of the water times G is equal to the volume of the ice times the density of the ice times G. And these G's cancel out, they're both just 9.8. And so what we wanted to work out was what fraction of the iceberg is underwater. So the volume found underwater is equal to the volume of the ice block times the density of the ice block divided by the density of water. So this the density of the ice block is 0.9167 divided by the density of water, which is 1. So this is 0.9167 times the volume of the ice block is the percentage that is underwater. So this tells us, to get it into a percentage, we times it by 100. So 0.9167 times 100 tells us that approximately 92% is underwater. Now with salt water, it's going to be a slightly lower percentage underwater because salt water is more dense than fresh water.
Let's do an experiment similar to what Archimedes did now. What we have here is a lump of metal. This is aluminium. Here I've got what's called a Newton spring balance. This will weigh the mass of this aluminium metal here. So we can lift it up and you can see on those scales that this has a mass of approximately 900 grams. Now what we're going to do is we're going to submerge this mass in the water. Now, according to Archimedes' principle, there should be a buoyancy force pushing up on this metal equal to the weight of the water displaced by the metal, which should mean that the scales read a lower number when this mass is submerged. So let's submerge it now. Now you can see on these scales, now that it's submerged, the scales are reading approximately 600 grams, suggesting that 300 grams or 300 millilitres of water has been displaced. So the water which has been displaced by this metal is gradually draining out of this beaker. So as soon as that's finished, we can read off the mass of the volume, the mass of the water in this beaker, which will be proportional to its volume. So let's read off that mass now. So the mass scales here, and the volume is saying 300. So 300 grams, 300 millilitres of water, which is the difference in the force recorded on this Newton spring balance here.
Special thanks to Sebastian Frick for filming this. Also thanks to these people who provided the images of the oil tankers that were used.